Welcome, and thank you for joining this webinar, Invisible Power, Infinite Scale, How Ambient Energy is Pushing the Battery-Free IoT World, prepared by Alpert research team. So if you only have microwatts of power, the communication method has to be just as revolutionary. That's near-zero energy communications, NZEC. What's the secret sauce there?
The goal is just radical power efficiency. We're aiming for peak power consumption well below 1 microwatt.
Backscatter eliminates the most power-hungry component of any traditional radio. So what is it doing differently from a normal radio?
A traditional radio is incredibly power hungry because it has to generate its own radio wave from scratch. It needs power amplifiers, frequency synthesizers. It's complex. Backscatter is the opposite. It's fundamentally passive.
It doesn't generate its own signal.
It doesn't. It simply modulates and reflects RF signals that are already in the air. From a TV station, a Wi-Fi router, a cell tower. It's borrowing the power in a carrier wave that's all around us, and that's what makes it orders of magnitude more efficient.
And there are a couple of different flavors of backscatter, right?
Yes, basically two main types, defined by how much power they use. The lowest power form is passive backscatter.
The purest form.
Right. The device just rapidly changes its antenna's impedance. It switches between being a mirror, reflecting the signal, and a sponge, absorbing it.
Yeah.
That switching action is how it encodes data, and it takes almost no energy.
And the other type?
That's semi-passive or active backscatter. It uses a little bit of that stored energy from its capacitor to actually amplify the signal it's reflecting.
So you're spending a bit of energy to get better range.
Better range or better reliability. It's a small power investment for a significant performance boost.
But let's clarify the difference between regular backscatter and the more advanced ambient backscattering.
The key difference is the source of the carrier wave. Standard backscatter needs a dedicated device to generate that carrier, which obviously costs power. Ambient backscattering is much more elegant. It piggybacks on pre-existing ambient RF signals. Anything that's a continuous wave, the device just modulates that signal. This completely eliminates the need for any dedicated carrier emitter, which is the ultimate goal of NZEC. But how does the device impose information, the modulation, with such minimal power consumption?
The device uses the simplest possible modulation schemes. Since it's only toggling impedance, complex phase or amplitude modulations like QPSK or QAM that require sophisticated oscillators are strictly avoided. Instead, simple techniques like on-off keying, OKM, or frequency shift keying, FSK, are used. OKey is the most common, where the device simply reflects the carrier wave for a 1 sweet and absorbs it for a 0.
Why add that extra layer of encoding overhead?
Manchester encoding is essential because it is self-clocking. It guarantees that there will be a voltage transition at the center of every bit period, regardless of whether you're sending a long string of 1s or 0s. And why is this crucial? Because AIoT tags use very cheap, inaccurate internal timing mechanisms. That guaranteed transition helps the receiver and the tag itself maintain chip-level time tracking.
So how does the reader, the base station or assist node, decode this incredibly faint reflected modulated signal?
The lowest power architecture used in the tag's receiver side, if it even has a receiver, is RF envelope detection, or RFED. This is a major efficiency gain. RFED receivers simply detect the amplitude changes, the envelope of the received RF signal. They are extremely simple, relying on a diode and a capacitor, and crucially, they eliminate the need for power-hungry components like a phase-locked loop or a local oscillator, dropping power consumption down to just a few microwatts.
But what is the unavoidable communication trade-off?
The major trade-off is range and sensitivity. Backscatter devices, due to the inverse fourth power relationship of signal decay, since the signal travels reader to tag and then tag to reader, are highly constrained. The incident carrier signal must be powerful enough both to harvest sufficient energy and to produce a detectable reflection. And the consequence of that is?
The consequence is, first, poor sensitivity around -40 dBm and a very high noise figure. But the real killer is its susceptibility to adjacent channel interference.
So any strong signal nearby can just overwhelm it.
Exactly. You can't tune it out. If you're in a licensed cellular band and a regular 5G phone powers up next to you, its strong signal will just saturate your receiver and completely block your communication. I think the key strategic takeaway is that shift in market dynamics. This technology fundamentally transforms what used to be an operational cost for a network operator, blasting out a radio signal, into a monetizable service, providing wireless power. This movement creates new ecosystems where the manufacturers and retailers who actually own the sensor data become the new data hubs. They create value in a way that's separate from just providing connectivity. It forces a total reassessment of where value lies in the entire IoT chain. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert research team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.